Okay, we'll go ahead and get started here. Again, good evening. Welcome to the USGS, to the monthly public lecture. I'm William Seelig. I'm with Science and Information Services. I'm glad to see everyone here for tonight's lecture. Just a quick reminder about next month. Our May lecture is Underwater Secrets of the Hayward Fault Zone, Integrated 3D Imaging to Understand Earthquake Hazards. You can pick up a flyer on the back table there. Tonight's lecture is, the title is Potential Corrosivity of Untreated Groundwater in the United States, presented by Ken Belitz. And a little bit about Ken. He is currently the chief for groundwater studies for the USGS NAQUA project, which is a component of the National Water Quality Program. Ken received his PhD in hydrogeology from Stanford University in 1985. Then after graduation, he worked for USGS California District for 5 years, was also a professor for 7 years, and then returned to the USGS in 1998. Ken has developed groundwater models. He's led the Santa Ana NAQUA study unit and the California Groundwater Ambient Monitoring Assessment, which is the GAMMA program. And he was also part of the team that developed the science and implementation plans for the third decade of NAQUA's activities. Ken and his co-authors have published more than 100 science publications and reports. And again, he's happy to be back here in Menlo Park for this lecture, and we're happy to have him here. So please give a warm welcome to Ken.
Thank you. As I said, I'm happy to be here because it's 45 degrees and raining in Massachusetts presently. As Will noted, the title of my talk is Potential Corrosivity of Untreated Groundwater in the United States. For those of you who are not familiar with the National Water Quality Assessment Project, it's a project that was initiated in 1991. The United States Congress asked the U.S. Geological Survey to assess the quality of the nation's water. Is it getting better or worse? And what are the factors affecting water quality? The work that I'm presenting today is part of that larger project. The motivation for our work was the occurrence of lead in drinking water in Flint, Michigan, which raised questions about the quality of drinking water elsewhere in the nation. This headline is a little bit more than a year old. USA Today noted that high lead levels were found in more than 2,000 water systems across the U.S. And that headline was based upon some EPA data that is publicly available. Well, as it turns out, media attention grew because there are comparable problems in many places, including large cities such as Washington, D.C., Philadelphia, and other water systems. Given the occurrence of these types of problems, congressional representatives, media approached the USGS asking questions like, well, where else in the nation might this occur? As the person responsible for groundwater quality investigations, we turned to look at groundwater. And to start, it's important to note that groundwater provides about 45% of the nation's drinking supply. For those of you who live here on the peninsula, most of your water is coming from surface water sources, not so much groundwater. A particular area of concern are private wells, because private wells are unregulated. I'm getting error messages here. Private wells are unregulated and largely unmonitored. The number of people on private wells is about 44 million people, so the potential exposure is possibly widespread. Well, given a problem of this magnitude, given the nature of groundwater, what can the USGS do to inform the public on this issue? The U.S. Geological Survey is an information agency. It's not a regulatory agency. We don't deliver water. We don't set the rules. Well, the USGS, however, does have a large data set. We have the ability to model, and we also have research capabilities which allow us to characterize source water quality. Source water is water before it gets delivered. After water is extracted from the ground, it can be treated, it can be blended, or otherwise changed. Similarly, surface water can undergo treatments. Source waters can include groundwater. They can include surface water. When we look at groundwater, the issue largely is how does water quality vary over space. When it comes to surface water, there's a question of how it varies over space, but also over time. So again, we're going to focus on groundwater. The data sets that we'll draw upon are in our National Water Information System, and the two largest sources of data into that system are our National Water Quality Assessment, or NAQWA program, initiated in 1991, and it's still ongoing into the present. We also have a cooperative water program where our water science centers work with local or state agencies to engage in local or state scale projects. When we collect those types of data, they're brought into our online data system. Well, so that's a little bit of background. So how can source water quality affect the occurrence of lead in household water supplies? So again, source water gets changed before it may come out the tap. There have been a large number of previous studies which clearly show that source water can interact with the pipes. So lead generally does not come out of the ground with the groundwater. If lead is present, it's because the groundwater has interacted with the pipes in the system. For example, there was a Virginia study by Piper and others. They sampled more than 2,100 private systems, and they found that nearly 20% of what they call first flush water exceeded 15 micrograms per liter, which is the EPA action level. By first flush, they mean you turn on that tap and the water comes out. If that first flush is in the morning when the water's been sitting in the pipes overnight, the concentrations can be a lot higher than later in the day. And if you let that water run, the concentrations can also drop. When a source water moves through pipes, if that source water contains calcium carbonate, it can deposit that calcium carbonate on the inside of the pipes. So many of you may have lived in places in the country with hard water. So you get buildup on your fixtures, you get buildup on the inside of your dishwasher, your pipes can get filled up. Generally, that's considered a nuisance or a problem, but it does have the benefit of lining the pipes. If the pipes are lined, then that water is not going to interact with the pipe. So it's a protective layer. In addition, the same minerals that are deposited in the inside of the pipes can also sequester lead. So lead carbonate can be sequestered along with calcium carbonate. So in addition to armoring the pipes, a water that tends to precipitate can also precipitate out lead minerals, and hence the water out the tap might not have it. With that said, if the water changes in that system, you can also flush some of those previously deposited minerals out. If the pipes are not lined and the water's in contact with those pipes, you can simply get dissolution. We've all seen it. You put salt in water, it disappears. If you put a piece of metal in that water, you may not think that the lead or other metals have gotten into the water, but small amounts have dissolved. Another way that lead can get into the water is if lead pipe is in contact with copper, or if copper pipe is in contact with lead solder. When you have two different metals, you have a difference in electrical potential, and you set up an electron flow, and you also set up an ion flow. When you have copper and lead, the lead sends electrons to the copper, and it also dissolves off lead ions. So it's just like your car battery, so that's galvanic corrosion. So if lead is present in the system, you can get galvanic corrosion. These three plots are taken from a paper by Hu and others. There's a group that operates out of Virginia that have done a lot of the work on lead in drinking water systems. And what this plot shows on the x-axis is time, on the y-axis lead concentrations. They took 3 different source waters. They labeled them here water A, B, and C. And they simply allowed that water to be in contact with lead pipe over a period of several weeks. Each week, they extracted a sample. They made a measurement of lead concentrations. And those red lines that you see all have concentrations on the order of 300 micrograms per liter. The EPA action level is 15. So if you have an aggressive water, simply allowing that water to be in contact with the pipe will put lead into the system. They then connected those lead pipes to copper and then did the same thing. And what they found is that the concentration increased by a factor of 3 to 15. And that increase in lead concentrations when copper is in contact with lead is galvanic corrosion. If you have a home that was built in the 1920s or previous, you might have some lead pipes. If you bought a home that was built as recently a few years ago, there's a good chance there's copper pipes, and copper pipes often have lead solder. It wasn't until the 1990s that lead solder was really eliminated from use. So that's just kind of a background. We can get lead in water, not because it was in the original source water, but because the source water interacts with the piping system. The quality of the water that extracts those metals is corrosion. So it doesn't have to be like an acid, where you're pouring acid on something, you just watch it dissolve. That term corrosion is just used generally to mean dissolution. In order to address the question, how can source water affect the occurrence of lead in household water supply, we utilized our data from our National Water Information System. It's one of the advantages of being a long-lasting agency that keeps records. These were data that we collected, and we limited our... What's that? Oh, sorry. Gotcha. We have data available from 27,000 locations, and we use two different indices of corrosion. One of these is called the Langelier Saturation Index, or LSI. The Langelier Saturation Index is essentially a calcite saturation index. It's a measure of the likelihood of calcium carbonate or scale to form on the inside of a pipe. Another measure is the potential to promote galvanic corrosion, or PPGC. It's a government agency. We have to use acronyms. And the potential to promote galvanic corrosion is a function of the chloride to sulfate mass ratio. That's because chloride is an electrolyte, and that helps carry that charge. The sulfate tends to suppress that. In addition to the chloride to sulfate mass ratio, the alkalinity of the water tends to suppress galvanic corrosion, and alkalinity is another way of looking at calcium carbonate. It's important to note that the corrosivity of the source water is one of many factors that can affect the occurrence of lead in household water supply. If you've got PVC pipes and your water is corrosive, you won't have lead. If the water is moving quickly through the system, you might not have lead. And similarly, the precipitation of minerals on the inside of the pipe is not just a question of calcium carbonate. There are other solids that can precipitate out. So there's more complexities than this might imply. It's important to note that the USGS typically samples at the wellhead, not at the tap. We sample public supply wells, so that picture on the left is one of our employees at a large public supply well. We sample domestic wells, and we sample observation wells. Public supply wells in most parts of the country are relatively deep. Here in California, a public supply well will generally draw water from depths of 200 to 500 feet from beneath the surface. There aren't a lot of domestic wells in this part of the world because it's so urbanized. In other places, domestic wells are present, and typically a domestic well will be drilled to a depth of about 100, perhaps 200 feet. Sometimes they're deeper, but that's a typical depth. Observation wells are drilled so that we can make observations. Typically, they're drilled shallow because there aren't supply wells, or they're drilled really deep because there aren't supply wells. After water comes out of a public supply well, or if it comes out of a domestic well, it can be treated. The picture on the left is a large treatment facility. The picture in the middle is a household treatment system of one of our USGS employees. And after that water comes out of the ground and before it comes out the tap, it can be treated. So the source water is not equal to the tap water. So again, the USGS evaluates the quality of untreated groundwater. Let's look at our first image that is a map of what we've done. And the question with regard to Langelier Saturation Index, or LSI, is to what extent might pipes be protected? We had sufficient data in our data set to look at 22,000 locations. The orange circles are groundwater samples which are potentially corrosive. They have a Langelier Saturation Index that's more negative than negative 0.5. The blue X's are groundwater samples which are potentially scaling. They have a Langelier Saturation Index, or LSI, greater than positive 0.5. Because of the complexities in actual mineral formation, values of the Langelier Saturation Index between negative 0.5 and positive 0.5 we'll call indeterminate. You really can't say that minerals are going to scale or not in that range. On a national basis, 32% of the sites are corrosive, 63% are indeterminate, we don't know, and 5% are scale forming. So on a national basis, we generally do not have scale-forming water. If you look at all those orange locations, if you look at New England, you look at the Mid-Atlantic, you look at the Southeast, you see a lot of orange. If you look at California, that orange field that you see there is the eastern San Joaquin Valley, the eastern Sacramento Valley, the Sierras. You look at the Pacific Northwest, there's a couple of valleys where we have those orange values. Now it's important to note that this map is very much controlled, or the look of this map is very much controlled by which dots you put on top. If you put the blue dots on top or if you put the gray dots on top, it changes the way it looks. So we like to quantify this so it's not just dependent upon how we plot the image. So what we're going to do is take all those data for each state and summarize it. And the first thing we'll do to summarize it is simply calculate for each state what is the average value of the Langolier saturation index. If the average value is more negative than 0.5, we'll color that state salmon. If the average value is greater than 0.5, we'll color that state blue. There are no blue states. If the average Langolier saturation index is between negative 0.5 and positive 0.5, we'll color it gray. It's indeterminate. So we've characterized each state on the basis of its average value. What we've also done is shown in pie charts what proportion of the sites or samples in a state are corrosive, indeterminate, and potentially scaling. And if you look at all those salmon-colored states, you see a lot of orange on all those pie charts. So the pie charts are a visual way of summarizing the information as well. The Pacific Northwest, we saw 2 states that are now salmon-colored. You'll notice California comes out in that indeterminate category. So even though there are some locations where the water is potentially corrosive, on a statewide basis for the sample set that we have, the state is indeterminate. You notice Hawaii, which is basalts, volcanic rocks, is also potentially corrosive. Let's take a closer look at California, since there's a California audience. We've taken the state and we've divided it up into what we'll call hydrogeologic provinces. We'll start in the northwest and we'll rotate clockwise. The Klamath Mountains, not a lot of folks live up there. The Modoc Plateau and Cascades, again, relatively unpopulated. The Sierra Nevada, a large number of vacation homes, a large amount of tourist industry. The Basin and Range, relatively lightly populated. The desert, which tends to be populated up against the mountain fronts that's separated from the LA Basin. Winding back up, the San Diego mountains and other areas in that southwestern corner of the state. The transverse and selected peninsula ranges includes the LA Basin, Orange County, the Inland Empire. That's the set of mountain ranges that tend to run west to east, whereas most of the mountains in the state tend to run north to south. The southern coast ranges, the Central Valley, the northern coast ranges. The map in the middle shows our point values. The orange circles are values more negative than 0.5. Langolier saturation index suggests potentially corrosive. The gray are indeterminate. And then you could see some blue values. There are not very many there, mostly in the LA Basin. Well, again, it's difficult to sort of synthesize that data up. So what we're going to do is, rather than summarize our data on a statewide scale, we'll summarize it on a province scale. So what we see is the northern coast ranges, the Modoc Plateau, the Klamath Mountains, the Sierras, and the Basin and Range, on the average, have Langolier saturation indices indicative of potentially corrosive water. Southern coast ranges, Central Valley, Southern California tend not to. So if you look at the Central Valley, it's colored gray. There's a slice of orange in there. But when you look at those values, you'll see the eastern San Joaquin, the eastern Sacramento Valley, if we were to subdivide that particular province, would likely show up as corrosive, the west side not so much. So that was the Langolier saturation index, a measure. Will the pipes tend to have a protective layer of scale, or otherwise known as a nuisance layer, since people generally don't like that? We're now going to look at the potential to promote galvanic corrosion, PPGC. Again, if you've got lead and copper in a system, copper pipes, lead solder, you have the potential for corrosion of the lead. We're going to evaluate our samples with respect to the chloride to sulfate mass ratio and the alkalinity. We're going to code a sample as either high, moderate, or low. The high values are shown in brown. The moderate values are shown in blue-green circles. The low values are shown in blue X's. The blue X's here are plotted on top. First of all, what you should see is a large field of blue-green circles across the entire domain. If we look at the 27,000 locations where we have data, 67% are moderate. I really want to emphasize something here. In the previous plot, the LSI, the Langolier saturation index, that middle category was indeterminate. We couldn't say one way or the other. But moderate doesn't mean good. Moderate means that there is a potential for galvanic corrosion. It's just not high. 8% of the sites are high, 26% are low. Look at New England, look at the Mid-Atlantic, look at the Southeast, Pacific Northwest. The same places where you saw the Langolier saturation index having potentially corrosive values, we see the potential to promote galvanic corrosion, likewise showing that as being relatively high. So again, we're going to summarize that data. It's hard to take all those point scales. Now we're dealing with categories rather than numbers. We can take the Langolier saturation index, just take an average value, but now we've got low, moderate, and high. So we're going to code our states as follows. If more than half the wells in a state are low, we'll categorize that state as low. There are only 6 states, the northern Midwest, or the northern Great Plains, and the Rocky Mountain states. So you see those 6 gray-colored states. If a state's not low, then it's either moderate or high. If more than 25% of the sites in a state are high, we'll characterize that state as a high state. So if you look at New England, you look at the Pacific, if you look at the Southeast, you'll see that those states get categorized as high. Most of the country is categorized as moderate. So again, that's not necessarily a good thing. When we've shown these maps, people tend to see that orange color. God forbid we should have made it red, and they really would have seen it. So we see a similar pattern, Northeast, Mid-Atlantic, Southeast. Again, let's take a look at California. Again, we have our provinces on the west. If you look at that middle image, you just see nearly every value in this state categorizes out as moderate. Every single one of our provinces at a province level categorizes out as moderate. If you look at the Sierras, you'll see there's a brown slice in there. So it doesn't mean that all parts of the Sierras are moderate. There is groundwater in the Sierras that if you put that water into a system that had copper pipe, lead solder, you could leach lead from that system. So we have 2 different indices, one measuring the potential for scaling, the other for the potential to promote galvanic corrosion. We're going to combine these 2 to get just an overall picture of what the nation looks like. We've got 3 categories for the LSI, Langolier Saturation Index, potentially corrosive, indeterminate, or scaling. For potential to promote galvanic corrosion, PPGC, we have high, moderate, and low. Let's start with this indeterminate category on the LSI. It's indeterminate. We really can't say one way or the other what's happening. Well, there are no states that are high on PPGC and moderate for indeterminate. There are no states that are low for PPGC and indeterminate. So since we can't make a statement based on LSI, then we'll inherit that classification. So if a state is moderate on PPGC, we'll call it moderate if it's indeterminate on LSI. It turns out, since we had no states that are scaling, so those are all not applicable. There are no combinations there. We go up one level from indeterminate to potentially corrosive on that LSI index. We're still in the moderate class. We'll classify that as high. Moving over to the left, a state is potentially corrosive. A state is high PPGC. We'll call that very high. So it's just kind of qualitative terms. And the color scheme we'll use is kind of that darker orange for very high, that medium orange for high, and a green for moderate. And then a low, it's indeterminate and it's low on the PPGC. So this is the sum of all that. So 27,000 data points. Make those calculations for Langolier saturation index, potential to promote galvanic corrosion, get those state summaries, combine the summaries. And then what we see, if we look again at New England, we see states coded as very high prevalence for the potential to have corrosion. Southeast, if we look at prevalent, then that area grows and covers the entire Atlantic seaboard, the Pacific Northwest, and Hawaii. 6 states get categorized out as low. They were indeterminate on the LSI. They were low, so therefore they stay low. Half of the country is in that moderate category. Well, what does this mean? Well, let's take a look at some numbers. If you look at those states with the darker orange, 8 million people have domestic wells that they depend upon for drinking water supply. If we look at the states colored in that lighter orange, that's 16 million people dependent on domestic wells. 24 million people live in states where the groundwater at a state scale is either high or very high prevalence for corrosion. If we look at those green states, the moderate ones, that's an additional 18 million people. If you look at those 6 states that have a low potential, there are 1 million people on domestic wells in those states. So of the 44 million people, the numbers don't add up because it's just round-off error. Of the 44 million people nationwide that depend on domestic wells for their source of water, only 1 million are not living in states where we have some kind of prevalence for corrosion. The results that I've just shared with you have been published in a set of USGS reports. There's a scientific investigations report. There are some data sets. Those data sets have all been released and made available to the public. We also have a website where I've given you this link. You can go to that site, download the report, download the data. These data have been downloaded. For example, Bloomberg downloaded these data along with other data sets and published it. This work has been picked up by the Boston Globe, CNBC. It's gotten a fair amount of coverage. Equally important, we have frequently asked questions on this website. My colleague Mike Woodside has put this site together. He's done a really nice job. And pretty much if you have a question, you might find an answer to it there. And if you don't have an answer to a question you're looking for, there's a long list of agencies, state, local, federal, and industry trade groups, all of whom are providing links. So I encourage you to take a look there. That's work that we've done. What I'd like to now do is sort of move forward to show you where we're heading. The first thing I'll do this evening is share with you a case study that comes from the Virginia Household Water Quality Program. Erin Ling works with that program and has kindly shared data with us. She and her colleagues have sampled households, 6,000 households in 81 counties in Virginia. And when they sample what they call first flush water. They go in the morning when that water has not been running, and they obtain a sample. They then let that water run for a while, and they sample it again. So let's do the following. We're going to take that data that they kindly shared with us, and on a county basis, we'll ask the question, what percentage of the samples have high concentrations of lead? And by high, we mean more than 15 micrograms per liter, the EPA action level. The x-axis divides the data into 6 categories based on those percentages. They are 10% increments. The y-axis is the number of counties that fall into that category. So let's start with 0. If a county falls into that 0 category, it means that there are no samples in that county with a high concentration of lead. There were 2 of 81 counties that fall into that. The most common category is the 10 to 20% range. Go to a county, collect the samples, calculate the percentage of samples with high concentrations of lead. If it's between 10 and 20% of the samples, then this county falls into that category. 37 of 81 categories of counties fall into that category. There's a county out there that has 44% of the samples with high concentrations of lead in first draw water. So that's a fairly high number. Well, that's sort of the bad news side of this. There's some good news in this. And some good news in this is if you let the water run 5-10 minutes. What I've done is taken the plot from the previous slide. I've pushed it up to the top here. There's only 2 counties where there were no samples with high concentrations. There were 30-plus counties in the 10 to 20% range. If you let the water run, 51 counties have water samples without detectable lead using the methods that they have. On the previous axis, the categories were every 10%. Now it's every 2%. So 15 counties are in the 0 to 2% range, 11 in the 2 to 4 range, 1 county in that 8 to 10% range. So in a way, it's good news. You've lowered the lead concentrations by letting the water run. But probably if you're one of those households that part of that 8 to 10%, and you're still having water in your glass with lead concentrations above 15 micrograms per liter. So it's sort of a good news and sort of a bad news type of story. Now what we're going to do is take this data set and ask the question, how do the indices that the USGS is using to map have relevance? Now in order to do that, we're going to look at the state of Virginia, which is shown in that blue highlight on top of the other states. And those color codes are hydrogeologic provinces. So just as we can identify hydrogeologic provinces in California, we can do the same elsewhere. Shown in that blue-green color is the Valley and Ridge. Shown in that darker gold is the Piedmont crystalline. These are hard rocks. Water largely comes out of fractures. And then in the lighter gold color is the North Atlantic coastal plain. Recall that the Langolier Saturation Index, the LSI, is a measure of the likelihood of depositing calcite scale. So a sample can be categorized as potentially corrosive, indeterminate, or scale-forming. The potential to promote galvanic corrosion, PPGC, is an indicator of whether or not when lead and copper are in contact, we'll get dissolution of that lead. The value of a sample can be characterized as high, moderate, or low, And again, I'll point out that that moderate value green is not the same as indeterminate. So let's start with the Piedmont crystalline. I've drawn a nice orange box, tried to match those colors. That pie chart under the LSI has a number posted on it, negative 2.3. That is the average value for the Langolier saturation index for all wells in the state of Virginia in the Piedmont crystalline. And there's more than 1,000 samples here, to give you some sense of the data set. The pie chart shows what proportion of those samples are more negative than 0.5. The gray shows what proportion are indeterminate. And I don't know that there's even a blue slice in there for scaling. The PPGC is categorical. The blue slice is the low values. A state or a province can be categorized as low if more than half the values in that state or province are low. Well, that's not more than half, that little blue slice. That orange value is, pretty large, not quite, probably 30, 40%. Moderate is more than half, but we can see that the high slice is more than 25%. So this province, Piedmont crystalline, is high for LSI. It's high for PPGC. So when we combine it, it's a very high province. Let's take a look now at the North Atlantic coastal plain. The average value for all the wells in Virginia in the Piedmont crystalline is negative 1.0. That's less than negative 0.5. So therefore, it's potentially corrosive. The pie slice is for high values is not 25%. The pie slice for low is not more than 50%, so it's moderate with respect to PPGC. We bring it together, it's high. Finally, let's look at the valley and ridge. The average value in the valley and ridge is negative 0.55 if you round to the 100th place, and it's negative 0.5 if you round to the 10th place. So it's pretty close to the border, but strictly speaking, more than half, either the average value is more negative than 0.5, it's potentially corrosive. Not more than half the values are low, so therefore it's not low. Less than 25% high, so it's also moderate. So it has a high combined index, but let's just say it's borderline, we're awfully close to negative 0.5. So we're going to color code that with our blue-green color rather than the orange color. Let's take a look at these average values for a second. Negative 2.3, negative 1, negative 0.5. A clear gradient in the average value. Look at the size of that orange slice. There's a clear gradient in how big that slice is. The Piedmont crystalline is the most corrosive, the Valley and Ridge least corrosive. North Atlantic coastal plain intermediate in Virginia. Now this is a complicated slide, so please bear with me as I walk you through it. We see in that blue-green color the Valley and Ridge. We see in the gold color the Piedmont crystalline. We see in the light orange, the light gold, the North Atlantic coastal plain. We have data for 81 counties, but 2 of those counties have fewer than 10 data points. So we're just going to kind of set those aside. We're going to look at what proportion of the samples in a county have concentrations above 15 micrograms per liter. Dark green is 0 to 10%. Red is more than 40%. Where you don't see any of these 5 colors is where we don't have sufficient data. So you can see that orange color coming through. That's a county where we don't have sufficient data. So let's start by looking at the Valley and Ridge. You can see a little bit of the green coming through where there's no data. You can see a little bit of the blue-green coming through where there's no data. Where you see white, there are other hydrogeologic provinces, but the picture starts to get really complicated when you start looking at really small pieces. The counties in Virginia tend to run with the grain of the topography, and so you can see the line of counties that fall in the Valley and Ridge along that arc. And what you see is that all of the counties in the Valley and Ridge are in the 2 categories, 0 to 10 and 10 to 20. The average LSI was negative 0.5. The one high value county sits in the Piedmont crystalline. That's the county with 44% of its samples in first flush water above 50 micrograms per liter. One orange county sort of sits on both sides, the Piedmont and crystalline and North Atlantic. The remaining orange counties sit within the Piedmont crystalline. If you look at the yellow counties, they largely sit in the Piedmont crystalline, but they also occur in the North Atlantic coastal plain. The Piedmont crystalline had a value I think it was negative 2.3. North Atlantic coastal plain was somewhere around negative 1. The indices that we've been using to map nationally, in fact, are correlating in this qualitative way with our county scale data. Well, why is that important? It's important because there isn't data for lead in tap water typically available in the United States. Virginia is an unusual state that they have such a proactive program in reaching out to domestic well owners. Public supply wells are regulated in the United States. As much as people might not like regulation, it means that those purveyors need to make measurements on their water samples. Sometimes the system fails, as we've seen, but by and large, it is protective. So this map showing the potential for corrosivity is what we have at this time. And we've seen in Virginia, which, by the way, is prevalent, not very high. It's just high, not very high. So there are states with potentially more corrosive water than Virginia. So what are the next steps? We would like to, in fact, we have developed alternative indices that directly address the potential occurrence of lead in water. And how do we do that? I put the word titrate in quotes. Titration is where you incrementally add small amounts of something to solution. So we're going to, quote, titrate lead into each of those 23,000 groundwater samples. Well, those groundwater samples only are on our computer. Those water samples have been long gone. Instead, we're running geochemical computational codes. David Parkhurst, one of the authors on this upcoming paper, was the author of an important program called Freak-C. He's been working with the senior author Brian Juergens, and we're mathematically titrating lead into our 23,000 samples, and we're asking the following question. How much lead goes into solution before it begins to precipitate? And we're going to call that the lead solubility potential. So if you can put a lot of lead into that water and nothing precipitates out, that water has a great capacity to dissolve lead. Otherwise, if it didn't have the ability to dissolve lead, it would precipitate. So those are aggressive waters. So here's an image of what that looks like. It's a preliminary image. This work is now in review. So the red values are sort of the top 10% of all the 20,000 plus samples that we have. Those are samples where you have to add 300 micrograms per liter or more before you see any lead precipitate out. So that's 20 times the EPA action level of 15. The green values that you see are samples where you would add somewhere between 15 and 300 micrograms per liter before you see the lead even begin to precipitate. The blue values are those samples where lead begins to precipitate before you have to add 15. So this is a more direct indication. Well, lo and behold, you see New England is no longer red, but there's still a lot of green there. You look at the Mid-Atlantic, you see a lot of red. You look down the rest of into the southeast, you see a lot of green, and you start picking up red again. Pacific Northwest, we see green. You see green in the Sierras. You see green in the eastern Central Valley. So the angular saturation index was seeing something comparable. Well, the next step includes looking at where in the U.S. are people dependent on domestic wells for drinking supply. Typically, these numbers are accumulated by agencies like the U.S. Geological Survey at the county scale. We've taken on this as a project using census data and road networks to look at where the people are who depend on domestic wells. The red values that you see are locations where there are more than 100 people per square kilometer with domestic wells. The blue values are places where there's one person per kilometer squared. The gray value is less than one, and in the white space, there are no people, basically, according to the Census Bureau, or they're too far from a road to likely be located. Well, let's compare for a moment this map of where the people are with the angular saturation index. If we look at that mid-Atlantic up towards New York, you see a large number of places where there's a large number of people on domestic wells. If you look at that LSI, angular saturation index map, the water is potentially corrosive. If you look in Colorado, you'll see there's a bunch of blues and greens, and that's a place also where there's some corrosive water. If you look in California, you'll see some orange and red. That's largely the eastern San Joaquin Valley, the eastern Sacramento Valley, the low Sierras. If you look at the angular saturation index, the LSI, you find potentially corrosive water. So we're beginning to put these data sets together. If we're going to make maps better than the states, what's the motivation for that? You saw in California that the provinces vary. You saw in Virginia that it matters where you are. The U.S. Geological Survey has mapped what they call principal aquifers. A principal aquifer is a large area of geological materials sharing age and lithology, which is important for water supply, either irrigation or drinking water. There are about 65 principal aquifers mapped by the USGS, and shown in these various colors other than the beige are 20 principal aquifers, which account for more than 90% of the water use in the United States. When you look at those beige areas, it includes about 40, 45 principal aquifers, but most of that beige area has not been identified as a principal aquifer. If we're going to provide a context for mapping, we need to characterize those areas. So we've also done that, and we're in the process of writing that up. So we can take that framework data, as I called it, the hydrogeologic framework. I've turned it on its side. I've shown depth in that third dimension. And I've shown depth because those hydrogeologic units do not occur uniformly as you go downward. They can have an outcrop area, and then they can plunge into the subsurface. So they have a three-dimensional shape, and we're mapping that. We have our population data. We have our new indices. There are additional factors that are also important, things like the age of the housing stock. We also have additional data available. The states have responsibility for regulating their water supply. That regulation requirement really stems from EPA. The states regulate the water supply. They require purveyors to sample those wells. They then tabulate those data. And nearly all 50 states have now shared their data with us. We will be able to bring into this analysis at least 100,000 additional data points to do this work. So we have additional factors, additional data, framework, population, new indices, and the goal is to bring it all together to identify risk. So let's summarize. Corrosive source water, if untreated, can dissolve lead from pipes and other components in water distribution systems. The USGS has prepared maps of potential corrosivity of untreated groundwater in the U.S. Untreated groundwater is not the same as tap water. The lead in people's glasses as it comes out the tap is not generally because that lead was present in the groundwater, but rather because the groundwater in contact with their plumbing systems extracted lead. We use the Langolier Saturation Index, LSI. It's a measure of calcite saturation. We have a new way to look at something called potential to promote galvanic corrosion, PPGC, based on chloride to sulfate mass ratio and alkalinity. We have a combined index based on a joint classification. Potentially corrosive groundwater occurs in all 50 states. 25 states were classified as high or very high prevalence. 24 million people depend on private wells in these states. We've published these data in scientific investigations reports, data releases. We have a website. I encourage you to visit that website. Our work is ongoing. Our work is ongoing with respect to corrosivity, but the National Water Quality Assessment Program has a broader mandate than corrosivity. We're looking at a large number of water quality issues as well. And with that, I'd be very happy to take questions.
All right. Thank you, Ken. Again, any questions for the audience? There are two mics toward the back. For the benefit of our streaming audience, please line up behind there or raise your hand, and I can bring you this hand mic as well.
You can tell us something about lead testing kits. How do you get them? How reliable are they? Should the public actually use them? Do they give reliable data?
I have not looked into the question of those kits. The Frequently Asked Questions website points towards a number of trade groups that probably, if you follow those links, you would be able to find something reliable.
Okay, thanks.
From a public health standpoint, are there public health departments that are reporting birth defects or learning disabilities associated with the areas that you have identified high lead or high potential for corrosivity in the groundwater?
Lead is a known neurotoxin which interferes with brain function, and there are strong correlations between lead levels in children's blood and their IQs. Lead in water is not the only vector by which children come into contact with lead.
That have public health departments in different states looked at your data?
Yes, the CDC has an environmental health unit, and these data have been loaded into that computer system.
I have two questions. Could you tell us about the current situation in Flint? And also for the homeowner, is there a way in which a type of filter could be installed in the main line to get rid of lead before the contaminated water comes into the house?
There are two questions. One question has to do with Flint.
Yeah.
Flint is a surface water story. It's a story of changing water supply. They change from one river source to another, and the treatment systems they put into place for the new water source were inappropriate for the water source. And then, of course, there's a lot of political/management issues associated with Flint. It's not a groundwater source type issue. With regard to filtering, there are ways to filter a supply, and I would encourage you to contact professionals. Professionals. There are people who can treat your water. Each case, will potentially be different. I don't think there's a generic solution.
So
Let me add one thing. You can overtreat your water. One of my colleagues, it's kind of typical. He had hard water. He decided to soften his water, and he figured if a little bit of softening is good, a lot of softening is better. And he had a new home with beautiful copper piping throughout the whole house, and then he noticed pinhole leaks. He had so treated his water that it aggressively attacked his copper pipes. So treatment is something requiring attention.
So in Flint today, is the situation cured, or is the water still contaminated?
I would refer you to the newspapers. I think the newspapers have a position on that without me having to weigh in.
We've had a refrigerator for years which has the purification canister. It seems to, when I read the information, it looks like it takes a lot of stuff out. Does it do anything for lead?
A lot of filters are charcoal filters. And charcoal
I have no idea.
And charcoal filters are good at grabbing organic compounds, getting at smaller molecules, smaller atoms, smaller ions is a bigger challenge. And so filters that filter metals in solution are not the same filters as you kind of find with a charcoal filter. There's usually more treatment involved in removing ions from water rather than
I guess what I'm asking you, is this thing doing any good? I use it for when I make coffee. I take the water out.
Much of the water in California, it depends on where you live in California. If you live in Southern California, the Colorado River is an important source of water supply. The Colorado River runs across agricultural fields, and there are pesticides routinely at very, very low concentrations, far below health thresholds. Carbon filters are very good at removing organic compounds from water. Hetch Hetchy is a relatively pristine water supply. So the need for filtering Hetch Hetchy water is not as great as the need for filtering Colorado River water. It is required by law for a public purveyor to deliver a water supply that meets standards. But of course, laws can be broken, right? It's against the law to speed, and yet people blow by me on the freeway. So, no laws are perfect, but public purveyors are required to deliver water that meet standards.
From what you said, then it sounds like having hard water is good. It tends to prevent the.
It will keep lead out of your water if nothing mobilizes that lead scale. So if somebody starts knocking on the pipes and bits of scale wind up in your glass and you don't filter those particulates, then you could ingest lead from the particulates.
Hi. I was wondering if the increase in fracking across the United States is creating havoc with your research and data, especially in the Montana and North Dakota regions, and, well, I guess Oklahoma, and even here in our state, where we are disturbing the aquifers deeply and bringing up radioactive and particles and everything else. I'm sure that it makes it very complicated for your research on everything.
Fracking is a kind of a catch-all term. So fracking is not just the breaking up of the rock.
The injection.
Right. I mean, there's all kinds of things associated with fracking. You have to build a road, you have to build pads, you have to dispose of fluids, you have to move the new petroleum. So there's a large number of potentially altering activities. And so you mentioned a lot of things which have impact. With regard to water quality, in most places so far, the depths at which they fracture the rock are deeper than the depths from which they extract drinking supply. And it takes time for water to move from deep to shallow. And the direct effects of sort of the breaking of the rock, the injection on that water quality, will take time to see. Certainly longer than the amount of time it takes for, say, a spill, which can then affect the supply. So depending on how you try to define the term fracking and what its impacts might be, it's a complicated, it's more than one question, maybe is one way of putting it, so there's more than one answer there. These samples that we've collected, date back to the 1990s. And we have some studies, and we're starting to publish. We will have sampled about 8 or 10 locations in the United States which are areas of active fracking. And we are evaluating the quality of water in domestic wells as a function of how far they are from those fracking operations. And those results will be forthcoming.
Any other questions from the audience? Oh, over here.
I just noticed these 3 southeastern states, Alabama, Georgia, and South Carolina, having a higher potential. What's behind? I may have missed it. But,
well, those 3 states, as well as some of those New England states, are getting their water from the North Atlantic coastal plain. Virginia is kind of a funny example because the North Atlantic coastal plain in Virginia doesn't have particularly corrosive water, but other parts of the North Atlantic coastal plain or the South Atlantic coastal plain are host to very corrosive water. It's sort of buried under New Jersey particularly has very corrosive groundwater under a very large proportion of its state. And it has to do with the mineralogy mostly. There's not a lot of buffering capacity in those sediments, so the water stays acidic in essence after it enters the ground.
Over here.
You talked about in 1990 is when lead soldering of copper pipes was changed. Was that because there was government regulation that came into place at that time?
Mm-hmm. Yes.
And are the states did the states do something different? Did they react stronger? Do you know anything about that?
I don't.
Okay, last call. Any other questions from the audience? Well, okay, once again, I want to thank everyone for coming. Please thank Ken Belitz. Thank you. Have a good night.
just heard that the other day. Oh, there's all sorts of